Good afternoon, everyone. Welcome to our talk series, Conversation with Women Role Models in STEM. Our guest today is Professor Gomathi Nageswaran, who is the professor and head of the Department of Chemistry at the Indian Institute of Space Science and Technology, IIST, Department of Space, Thiruvananthapuram. So I will start by giving our audience a brief introduction about our organization. Pune Knowledge Cluster has been established by the Office of the Principal Scientific Advisor to the Government of India. It aims to bring together academia, R&D institutions, and industries in and around Pune to address some of the challenging problems of the region through innovative means and using scientific approaches, engaging highly skilled human resources. We host this monthly talk series as part of our Vigyan mentorship and scholarship program, which is an initiative for promoting chemistry amongst young women. This program is supported by BASF Chemicals India Private Limited, and it is implemented by us since 2022. So through this talk series, we aim to bring forward the journey of leading women in various fields of science, technology, engineering, and mathematics. We hope this initiative will inspire young women to break gender stereotypes, societal barriers, and encourage them to pursue careers in STEM. I now take this opportunity to briefly introduce our speaker. Professor Gomathi Nageswaran joined IIST in 2010. She has done her B.Tech from Madras University, her M.Tech in Chemical Engineering from Bharathiyar University, and a Ph.D. from IIT Kharagpur. She has over 20 years of teaching experience, including 14 years of supervising doctoral researchers. Her current research is related to metal organic framework, MOFs, for electrochemical sensors, electrocatalytic water splitting, carbon capture, membrane separation, and nanocomposites. She has published more than 40 research and review articles in international peer-reviewed journals, 6 book chapters, and also co-authored a book titled Metal Organic Framework Derived Materials, Design, Strategies, and Applications. She has attended several invited talks at national and international forums, and in her talk today, she will be discussing about her research in cutting-edge electrochemical sensing and carbon capture technologies. She aims to provide insights into the useful applications of these technologies. Also, she will be sharing her perspective on some of the challenges faced by women in pursuing research careers in STEM fields. Her talk today is titled Advancing Materials Science, a Journey of Research and Inspiration. Now, before I get started, I'd like to give a few instructions for the session. So we will have a 45 minutes presentation for our guest speaker. This will be followed by a moderated session. And after that, we will open the session for the audience for Q&A. So we have a link in the chat box for filling this feedback form. That will be towards the end of the session. Please note that we will be sending certificates for this session after the talk is over, but only for those candidates who are going to send us their feedback forms. Okay, so please do fill in those feedback forms. And yeah, so I am done. With this, I extend a very warm welcome once again to Professor Gomathi Nageswaran and invite her to take the session forward. Over to you, ma'am.
Yeah. Thank you, Ms. Ritika. Yeah.
Yes,
let me share my slides.
Yes.
Yeah. Are you able to see the slides now?
Yes, ma'am.
Okay. Yeah. Good afternoon, everyone. And first of all, I would like to thank Ms. Ritika for inviting me to be a part of this PKC talk series in conversation with women role models in SDM. So, like maybe before. Okay, so before moving to my talk, let me say a few words about our institute. So I'm from Indian Institute of Space Science and Technology. I don't know how many of you are aware about this institute. So this is coming under a Department of Space, and IIST was established in 2007. Especially this was to provide young talents to ISRO community. So that was the purpose of establishing this institute, and this is of one of its kind, like because this complete curriculum, it's mainly focusing on ISRO's requirement. And earlier the system was like the students got admitted to B.Tech program. They were like recruited as scientists in ISRO, and it was completely like a free education. So that was the system before, and now it is slightly changed. So the students are admitted through this IIT JEE advanced exam. And of course, they are given preference based on the ISRO's requirement. They'll be given preference for being called for this interview and all. Otherwise, the entry to ISRO as scientist is through national level exam through this ICRB. So now these students will be considered for being called for the interview. So that's for how the B.Tech program runs here. And M.Tech, it is admission is through GATE score, and the Ph.D is through national level eligibility examination, and also IIST is conducting its own examination through which PhD students are admitted. And of course, we have the privilege of having Dr. APJ Abdul Kalam as our first chancellor. So with this introduction to our institute, like I'll move to the talk on advancing material science, journey of research and inspiration. So our group is mainly working on materials. Yeah. So the materials like you can see here, like we have, our group has developed materials for various applications covering the areas including catalysis, adsorption, sensing, water purification, and space application for space applications, and aerospace structural application. And so here, like in the catalysis, we like this heterogeneous catalysis part, we just collaborated with another group here. Otherwise, like our group is focusing on this electrocatalysis. Mainly it is for the water splitting reaction, like where we are developing the materials, electrode materials for enhancing the hydrogen evolution reaction and the oxygen evolution reaction. And that is like the focus on this. This is mostly MOF based material. So I'll just discuss about what is MOF and its application. But with respect to the sensing, I'll be discussing today. And adsorption, we focus on adsorptive removal of various emerging contaminants from water, and also carbon capture. So that's again like MOF based materials we are working on. And sensing, we are working on both electrochemical sensor and fluorescent sensor. And in fluorescent sensor, we worked on this inorganic quantum dots. And also currently we are focusing on luminescent MOF-based materials for fluorescent sensing applications. And in electrochemical sensor, like we worked on this graphene-based sensor, and currently we are focusing on MOF-based electrode material for electrochemical sensing of various analytes. And yet another application our group is focusing on is water purification for space application. So this is mainly like for maybe like manned space mission and all. Like we cannot the purified water because we'll have limited access to water only. So like what all the possible water should be collected and purified and should be reused. So like in that case, the purification process involves several stages, and we are focusing on, in the sense like how to remove the contaminants maybe through the adsorption process. So currently in like ISS and all, they are using that zeolite based bed, and which we are aiming to replace it with and ion exchange bed also. So which we are aiming to replace with like a MOF based material. And also we have proposed on this another special membrane called aquaporine membrane, which can be used for purification of water. And another area is aerospace structural application. So in the structural application, it's mainly like two areas we are focusing on. One is like to like manufacture this, what to say that, to develop this composite polymeric material. And like because structural material, like when it is used in the space environment, it has a problem of like static charging, electrostatic charging. So to prevent that, some conducting materials are incorporated onto this polymeric matrix. And so one such material is carbon nanotube. But the problem with the nanomaterials is they will have the tendency to get aggregated. So to prevent this aggregation, like we modify this carbon nanotube material through plasma treatment, and then it is dispersed in the polymeric matrix to enhance its dispersion, so that we can prevent the aggregation of this CNTs. And another application is like in the high temperature applications, like carbon foam. So in which we'll be using that porous carbon free foam, which is deposited with carbon by chemical vapor infiltration process. So these are the broad overview of the research activities happening in our group. And for today's talk, I'll be focusing on this adsorption and sensing. And again, in the sensing, only this part, electrochemical sensor part, I'll be discussing. So these two areas I'll be focusing on today's talk. And maybe like this is the first maybe a work like I'll be discussing on, and this is graphene based material for electrochemical sensing applications. I'll just all these I have put in one single slide. This is my first PhD student's work, Dr. Lavanya, who is now assistant professor in Satyabama University. And so this is like mostly all these are like variants of this graphene. So the graphene was further modified to enhance its performance for sensing of various analytes. So you know that the graphene is a two-dimensional nanomaterial which can be obtained from graphite if it is by top-down method, and it can also be synthesized by bottom-up method also. But we synthesized this graphene by top-down method from this graphite. It is by chemical exfoliation method. And but the problem with this, actually graphene as a single layer, like one layer of this two-dimensional graphene, it has all excellent properties in terms of its extremely high electrical conductivity or thermal conductivity or mechanical strength and large surface area. So it has all excellent properties. But when we are exfoliating this graphite to get this few layered graphene structure, the problem is they will have the tendency to get restacked. So we have to find some way to prevent this restacking. And the chemical method of this exfoliation of this graphite to obtain this graphene, it's very, because that is by oxidizing this graphite. So during this oxidation process, like the oxygen containing functional groups will be exfoliating. So that will be placed between the layers. And during reduction process, subsequent reduction process will remove all the oxygen containing groups. But it's not complete reduction happening. So usually that chemically obtained graphene, that is named as RGO, reduced graphene oxide, because graphene oxide is reduced, which still have some residual oxygen containing groups. So to further enhance its properties, we follow different strategies so that it can be used for sensing of various analytes. So the first strategy what we have tried was, the thing is like graphene, after it is exfoliated to obtain this few layers, the problem is they will have the tendency to get restacked because of pi-pi interaction or this van der Waals force. So to prevent this, because once it is restacked, then that behaves something close to this graphite structure. So all those excellent properties will be lost. So to prevent this restacking of these graphene layers, exfoliated graphene layers, we have to keep some space. So here what we tried was, between the graphene sheets, we placed graphene nano ribbon. So this graphene nanoribbon acted as a spacer molecule, which helped in keeping the graphene layers separated. And that material was used as an electrode material for electrochemical sensing of ascorbic acid. That is nothing but vitamin C. And it showed a promising result. And then we further modified that material. Maybe as we can see here, this GNR is the hybrid material, which was further treated by this nitrogen organ plasma. So which incorporated this nitrogen containing group, which helped in enhancing its electrocatalytic property. And what we have observed is the same material now could be used for the simultaneous detection of ascorbic acid, dopamine, and uric acid with a better sensing parameters, with a better performance. And that simple RGO in another work, we modified by plasma treatment. That is ammonia plasma treatment. That's again a way of introducing this nitrogen containing groups, and it was used for the detection of nitrite. And in another work, the same hybrid graphene, this graphene sheet and graphene nanoribbon. So this hybrid graphene was incorporated with nickel nanoparticle. So the nickel is one of the important catalyst for the detection of glucose. So this particular material we have applied for the electrochemical detection of glucose. And the point to be noted is this is a non-enzymatic glucose sensor, because otherwise mostly you must have seen this glucometer, which is commercially available in the market, but they are all like enzymatic like method. But here the electrode is non-enzymatic one. So that's the advantage, but still it was showing the performance comparable to that of this commercially available glucometer. And in the other work here, like we used this gold nanoparticle was incorporated onto this graphene nanoribbon, and it was used for the detection of the cancer cells. So this is the overview of like what we have done on this graphene based material for electrochemical sensing of various analyte, which was done by Dr. Lavanya. So why I started with this work is like Dr. Lavanya, maybe we can say that she is an inspiration for her juniors, because when she started her PhD, like during her journey of the PhD, like she got married and she had a baby also. But like one can understand the difficulty in managing both this research as well as this family. It's not that easy, but she managed very well. I could also connect with her very well, because I also did the same thing. Like when I was doing my PhD, I started my PhD journey when my son was 2 years old. So my PhD, the whole PhD went like if the babysitter comes, then I can go to the lab. So that is all. So that's the, maybe I would say that that is one of the major challenges with respect to women, like when they want to like pursue their research, not only for the research, for any career, like for their career, the work-life balance for especially women, it is much more like maybe complex or much more difficult compared to men, because men may not have they will not have much what to say that more responsibilities, but still like society expect us to, and also we prefer to like keep that whatever that responsibility. So that's the one of the major challenges. But one thing is like if you are determined, then nothing can stop you. So that is like I could understand from my students' work as well. And so currently, most of our work is like focusing on the material called metal organic framework. So the metal organic framework is an emerging porous crystalline material. And so as you can see here, this metal organic framework, it's a framework structure which is formed by this metal ions or clusters which are present in the nodes, and they are connected by this organic linkers or the struts. So as you can see, this metal ions or clusters are connected by the linker molecule, organic linker molecules. So this forms the complete framework structure. And the beauty of this MOF material is like the porosity of this material is highly tunable. So we can tune the pore size or pore volume, whatever. And even the catalytic property can also be tuned by choosing the appropriate metal node and the linker molecule. Say, for example, if you are choosing a larger organic ligand, then your pore size will be large, because the organic linker molecule is what is separating these two metal nodes. So the size of this linker molecule will decide the pore size. So that is how we can actually tune the porosity of this MOF structure by choosing the appropriate linker. And also, most of the cases, this catalytic property depends on the metal nodes. So this metal node also, depending on the application, we can choose the a suitable metal node. And another thing is as you can see here, it's not not only that MOF material alone, we can even go for it's a hybrid material. So some other material, like it can be a secondary ligand, or it can be some other material, kind of maybe carbon nanotube or graphene, so these different other nanoparticles. So they can also be hybridized with this MOF material with these different modes. Either the second material, it can be hybridized by it can be bonded with this metal. It can interact with this metal node, or it can interact with the linker molecule, or it can be encapsulated, or it can be a kind of a layered structure. So there are different modes by which we can hybridize the MOF with other materials. And so as you can see here, this is MOF material, and it is composited with various material, or we can even derive the other materials from MOF. In the sense, maybe this carbon nanotube can be derived from MOF material, or metal oxide or nanoparticles can be derived, and carbon can be derived. So there are different materials that can be derived from this MOF. And so they can also, because say for example, the carbon derived from MOF material. So the thing is, this complete structure will be carbonized. So during this carbonization, maybe this metal can be removed by acid washing and all. And then during the carbon obtained by carbonizing this MOF structure, the advantage is whatever this porous structure, that will be retained. So the pore structure, that porosity, will be helpful in the respective application. So all this different 2D MOF or defective MOF, what they mean here is, so here this metal node is coordinated with the linker molecule. There may be some sites where this coordination is missing. So this defective sites or active sites for certain applications. So that is what is this defective MOF means, and its derivatives, composites. Multivariate MOFs means instead of using one metal, you can even go for bimetal. So instead of one metal being used in this node, maybe here you can have copper, and here you can have ruthenium, or here you can have gold or silver, so that way you can nickel. So there are different metals can be used, so that also has its own advantage. So these kind of different MOFs or its derivatives or composites or the post-synthetically modified MOF materials, they find application in all these areas photon conductivity, biomedicine, chemical sensor, heterogeneous catalysis, gas storage and separation. So these are the various applications. And we are focusing on, as I said, this chemical sensor and this separation, in the sense maybe adsorption. Okay, so that is the areas, and also catalysis, electrocatalysis is another area we are focusing on. And for this electrochemical sensor, it is mostly you will have this catalyst material will be coated on this is your electrode material. So in our case, this is MOF material. So when it is in contact with that sample analyte, in the sense this analyte will have that is in the presence of various other molecules as well, but it will selectively interact with the analyte of our interest, and the response will be mostly depending on which type of sensing mechanism is used. If it is a potentiometric sensor, for the applied potential, the current produced will be measured. And in amperometric sensor, this is the potential, there is a potential window, and with increasing potential, like how the current is produced. So that will be recorded. And whereas in the amperometric sensor, at a particular potential with increasing time, how the current is produced in the presence of analyte. So this is like whenever you are adding this analyte. So what you can see here is that step increase. So every step is corresponding to the increase in the concentration of that particular analyte. So that also how much current is produced with increase in the concentration of the analyte, that can be recorded. And this is impedimetric, this is something similar to that EIS. So this is like a resistance image, and real values of the impedance values will be plotted here. So this is depending on the different methods, the signal, whatever is recorded, will change. So here, I'm not able to see the title. Okay, so here it is like we are, this particular material is a bimetallic MOF material, which was used for the detection of the ciprofloxacin. So the ciprofloxacin, it's an antibiotic. And the thing is like, which is widely used drug in the treatment of this urinary tract, respiratory, and gastrointestinal and skin infections. So for these reasons, like ciprofloxacin is widely used. But the thing is like, and nowadays actually all these drugs are now recently considered as a contaminant. So they are emerging contaminants, and the presence of these drugs are not preferable basically. Like, because say for example, this antibiotic is mixed up with this maybe sewage treatment or like whatever the water, and then slowly like it will develop the resistance to these antibiotics. The microorganisms will develop resistance to this antibiotic. So which is not preferable. And also it's nitrogen cycle and all will be affected. And so that's why like that pharmaceutical residues in the environment is recently being considered as an emerging contaminant. So and we are here like, so the detection of these antibiotics becomes essential. And here what we did was like we synthesized this copper, like in the metal node we have copper, and this is the linker molecule, trimesic acid. So these are the precursors for this metal and the organic linker. This was synthesized at room temperature. And when this copper TMA was synthesized, actually it was having the rectangular, its morphology was in rectangular shape. And it was post-synthetically modified in the sense like after synthesizing this copper trimesic acid, then we added the precursor for the second metal, which is ruthenium chloride. So now what happened? We got this bimetallic MOF, that is ruthenium copper trimesic acid. And maybe you can see the same image of this. So this is the copper trimesic acid MOF material. Whereas after incorporation of this ruthenium, its morphology got changed to the triangular structure. So maybe this XRD, whatever, it is, there is no change observed with in XRD after addition of this second metal, which confirms that the crystallinity is not altered. It still retains the crystalline structure, but only the morphology is changed. And maybe the incorporation of that second metal is confirmed from this like XPS. So from this survey spectrum, you can see the presence of this ruthenium, which confirms the like incorporation of this ruthenium, and copper also you can see. So the presence of both ruthenium and the copper confirms the formation of this, the presence of both the metals. But we need to confirm whether this ruthenium is present in the form of nano material or nanoparticle, or it is integrated part of this MOF material. So here from this ruthenium, whatever the peaks we observed for this ruthenium 3p peaks were 1/2 and 3/2. So the presence of these peaks at this position, this is corresponding to the ruthenium in the oxidized state. Like it is not present in the neutral state. So that confirms the what to say that both this ruthenium 3D also. So it confirms there is no ruthenium nanoparticle added to this structure. So what happens to that ruthenium is actually it replaces the copper from the nodal point. So that is how it forms the bimetallic MOF material here. And it was tested for its electrocatalytic application. So here we can the electrocatalytic behavior, we can see compared to this copper TMA, after adding that secondary metal, it is enhanced. This is for the detection of this in the presence of ciprofloxacin. And like what we can see here from these two, comparing these two material, the peak current is increased. When it is copper trimesic acid MOF alone, the peak current is 36.1 microampere. But after addition of this ruthenium to the nodal point with this bimetallic MOF, peak current is enhanced to 74.8. So significant enhancement in the peak current is observed with the addition of ruthenium to the nodal point. And also this peak separation, that delta, that separation potential is also decreased after this addition of this secondary metal. And another thing, like what we can see, this charge transfer resistance is also decreased, that which indicates that conductivity, electrical conductivity of this electrode material got enhanced after the addition of this ruthenium to the copper TMA MOF material. And then this for calculating this electrochemical surface area, it was done at that, whatever that CV was done at different scan rate, and using the calibration plot, using that plot of which is plotted between that square root of that scan rate and the peak current. So using this from the slope, it was the ECSA was calculated, and even this ECSA was also found to be increased with compared to the copper TMA, or compared to this simply like a glassy carbon electrode. So which confirms the enhanced performance of the addition of that secondary metal. And so for this is again what is it this compares the DPV studies for bare glassy carbon electrode, and this glassy carbon electrode was coated with copper TMA, which showed some enhanced current with the addition of this ciprofloxacin. And glassy carbon electrode, when it was coated with ruthenium copper TMA, we could find still enhanced current, which indicates the enhanced performance with the addition of the second metal to this MOF material. And with a different concentration, this is the scan rate to understand the rate limiting step. So it was diffusion controlled process, which is understood from this plot between this peak current and the square root of scan rate, which gives that straight line. So which indicates that the overall process that is happening at the interface between the electrode and the electrolyte is diffusion controlled. And okay. So then the DPV was performed for the different concentration of this ciprofloxacin. So from this peak, the calibration plot was obtained. And what was noticed is that linear range. That means this particular electrode, this ruthenium copper TMA bimetallic MOF, this can be used for the detection of ciprofloxacin for the range of 2.5 to 100 micromolar. So for this range of concentration, we can use this electrode material so that we can find any unknown concentration of that ciprofloxacin within this range. And from this, we could also find that limit of detection as 3.29 nanomolar. And also the other sensing parameters, these are the interference studies with the possible expected interference. So usually not only the ciprofloxacin, so many other analytes can also, they are also expected to respond to that potential window. So these are the possible interference expected. But what we could see is they're not significant, like whatever the current produced by these interference are not that significant. So it is selectively detecting ciprofloxacin. And stability of this material was also studied by performing the CV for number of cycles. Like after 50 cycles also, there was not much change in the peak current. And only some 14% reduction was there. And again, like DP was also performed for 60 times. So even after 60th response, like the reduction is only about 7.4% or so. So not much reduction in its performance, even with more cycles or number of times when it was detected. And reproducibility, like it was the same material was drop casted on 6 different electrodes, and its performance was analyzed, and it was like almost everything was giving a same result. And in the next work, like the same copper MOF, we have whatever we have synthesized by room temperature process, like this was again like we have added silver to this copper MOF. So the difference is, in the previous work, whatever the ruthenium which was incorporated onto the copper, it was incorporated in the node. So that is the integral part of that MOF. So in the sense that MOF in its framework, so some of the nodes will have copper and some of the nodes will have ruthenium. So that ruthenium was added to the framework structure itself. So it was occupying, it was either replacing that copper. So that is how the ruthenium was incorporated onto the like a beam of structure in the previous work. But here, that silver is added to this copper MOF in the form of nanoparticle, and it was used for the detection of this levofloxacin. And whatever this is the copper MOF, as we can see here, the flake-like structure is corresponding to this copper MOF. And this is again room temperature synthesis. And when the silver particles or nanoparticles are incorporated, so you can see the distribution of the silver nanoparticles amongst this what is it, like this copper MOF nanoflake structure. And what we could see from XRD is the peaks corresponding to that silver nanoparticles were observed. So which confirms that silver is added to this copper MOF in the form of nanoparticle. And maybe the same with XPS also, we could find the presence of this silver and the copper. And then this silver, it is whatever the peak corresponding to this, this is corresponding to the silver in zero state, that is like nanoparticle state. And this material we have used for the detection of levofloxacin. So again, that CV was performed and what we could notice, this is for the bare GC, glassy carbon electrode. We are not getting any peak. So this is redox peak we could obtain for this copper, which got enhanced after adding this silver nanoparticle. So as you can see here, the peak current is increased from 25 to close to 60. And this peak separation potential is also increased. Okay. And another thing is like this RCT value, this is the which is obtained from this EAS spectra. We could see that charge transfer resistances decreased significantly, which helps in enhancing its performance. And then this DPV was performed to understand the enhancement in the performance after adding the silver nanoparticle, which is evident. In addition to that CV, this DPV was also performed. And then again, to understand that kinetics part at different scan rate, the same study was performed. And so from this, we could understand the like rate limiting step, which is again diffusion control, which is evident from this straight line obtained from the plot between this peak current and the square root of scan rate. And then for the calibration plot, DPV was performed for different concentrations of this levofloxacin. And whatever the linear range we got was for 1 to 95 micromolar with the limit of detection of 480 nanomolar. And again, the other parameters like the selectivity, stability, or repeatability and reproducibility were performed. So the selectivity with respect to this other interference, like there is no response or significant current signal was produced with the presence of this interference. It's selectively detecting this levofloxacin. And even that stability was studied after 50 cycles. There is not much reduction in the current signal. And again, for repeatability, it was repeated for a number of cycles. And even after 50 cycles, like the reduction in the current is very minimal, very marginal. And reproducibility, again, with 6 electrodes, it was performed. And there is not much difference in the current signal produced. So from these two studies, like, we could understand how this MOF can be modified further, like to enhance its electrochemical activity for the detection of these. Here, what we have discussed is antibiotic. And the next work will be focusing on the carbon capture. So this carbon footprint, maybe this is one of the terminal carbon footprint you must have heard several, like, because that is like bothering the climate issues and all, like, because global warming, it's one of the major environmental issue. Global warming, it's a global issue, like. So this carbon footprint, that is the total amount of CO2 and methane generated by our actions. But actually this carbon footprint, this term was coined by British Petroleum, and which is the second largest non-state owned oil company in the world. And they have 18,700 gas and service stations worldwide. And so it is like also claimed that going to work or buying food and traveling is also largely responsible for heating the globe. And there is also some people claim that this, whatever this carbon footprint, that's a kind of scam, in the sense British Petroleum, they coined this term just to divert like, in the sense they make public people responsible for this global warming. Mostly it is the industries, like from where this whatever this carbon dioxide or other flue gases are emitted, that largely pollute environment. But it is also said that some people say that whatever this carbon footprint, it is coined by this British Petroleum just to divert the responsibility of this global warming, to make the public responsible, not only the industries, it's the public's responsibility, kind of. And do you know, like, even whatever the modern life, where we are using the smartphone or computer, like internet usage, each and each and everything, like the digital world, definitely is contributing to this global warming. Because so the 70 kg of CO2 is released from mobile phone, means smartphone means, but the thing is 85% of the CO2 emitted from this smartphone, that happens during its production. So 85% of its lifetime emission is during production. So the remaining 50% only is emitted during usage. But if you look into this carbon footprint of internet use, so this accounts for like maybe ranging between 2.5 and 3.7% of global greenhouse gas emission. Actually, this carbon footprint from this internet usage, this exceeds those of aviation industry. So as you can see here, internet global footprint is 4%. And sending an email, it produces 0.3 gram of CO2. And maybe sending an email with attachment means approximately 50 grams. And 30 mails, if it is sent, it is producing 135 kg of carbon dioxide. But aviation produces only 2%. So that's why it is said that internet usage emits much more like carbon dioxide than even this aviation. So that's why, like, nowadays people are recommending for this National Day of Unplugging or World Digital Detox Day or Screen Free Week, self-imposed non-screen days and screen days. So this helps in minimizing the CO2 emission, and also it helps in helps for the better mental well-being as well. And another carbon dioxide emission is like you can see this picture. So that you can see the several racks. This is at the metadata center in Princeville, I think. So in US, like what you can see, that is with undeleted emails going back years and trillions of forgotten photographs, they are stored in the cloud, which make us guilty. That means, so if any unwanted mail is there, it's our responsibility to delete all those mails, because otherwise all those data will be stored, and to store that huge data, then the data center requirement will also be huge. So to maintain this data center, it consumes lot of energy. So maybe it's again like if you see this carbon footprint of internet, here you can see. So the user network equipment, it emits only 4% CO2. And data network, including this undersea cabling or core network and all, it removes only 10% of CO2. But the remaining 86% of this carbon emission is CO2 emission is from the data center, because to maintain the data center, it requires large amount of energy, which is mostly from the fossil fuel. So sorry, this is the same one, from which what you can understand is like carbon dioxide emission from the individual is also high. Like maybe this also gives you the idea, like China, 27% of carbon dioxide is emitted, that is when the global emission, 27% contribution is from China, and India 6.878% of the CO2 emission contributing to the global emission. So this is the data. So from which you can understand that CO2 emission is to be controlled, because that is one of the major greenhouse gases causing this global warming. So CO2 has to be removed from the atmosphere. It has to be captured from the atmosphere. So this carbon capture, so that is one of the major research area where people are working still on finding the suitable adsorbent which can capture this carbon dioxide. And this is again like another application of like where we really want this carbon capture is for manned space mission. See the concentration of this carbon dioxide, as you can see here, like when the concentration of this carbon dioxide increases. So these are the various impacts. Visual impact, like it dimmed sight with concentration of 8% of carbon dioxide in air atmosphere, and reduced hearing like with 3% of carbon dioxide in atmosphere. So these are the impacts of the increased concentration of carbon dioxide in atmosphere. So from which you can understand that to maintain the concentration of this carbon dioxide in maybe the living space is much more important, and especially for the manned space mission, we have to provide them the breathable environment. So for which currently they are using this absorption CO2 absorption bed. So it's mostly like kind of like for the removal of the CO2, the more efficient way of removal is using amine based absorption mechanism. But amine, it is corrosive in nature, and the regeneration of amine is also very difficult. So now maybe the new generation material for this carbon capture is MOF based material. And MOF based material again, so here we used MOF, but again we used bimetallic MOF. So when you are incorporating that second metal, so as you can see here, addition of that second metal can be in that same node, or this is completely one metal node and the other one is second metal. So these are the different ways how these metal nodes can be introduced onto the MOF structure. So this helps in increasing the stability and enhanced adsorption capacity, selectivity, tunable properties are possible. So these are the like different reasons like we go for this second metal with respect to this adsorption application. And also it we composited with activated carbon. So here the material what we tried for this carbon capture was we synthesized, everything was one part solvothermal synthesis. So here, this is this is the MOF material, which is the copper-based MOF material. And again, this copper was added with the second metal nickel, and then it was composited with what is it, like activated carbon. Okay, so we tried with monometal, bimetal, and monometal composited with activated carbon and bimetal composited. So this is monometal MOF, and this is bimetal MOF, where copper and nickel are there. Copper precursor, nickel precursor, and organic linker. So all these were put together and autoclave synthesized by this one part solvothermal. In monometallic MOF, copper precursor, organic linker, they were synthesized together. And then this is copper precursor, linker molecule, activated carbon. These are all put together and synthesized. And another material is copper precursor, nickel precursor, linker molecule, activated carbon. So these are the 4 different materials we tried and compared for their adsorption capacity. And maybe here, like you can see, this is the process. Okay, so this is the structure, paddle wheel structure. And this is our material, bimetallic material, maybe you can see here. So this is before drying, you will have the solvent molecules, and after drying, this is the solvent molecule. So the solvent molecules will be removed, and which makes this material we get this unoccupied. These are the metal sites. So these are unoccupied metal sites, and these are the sites available for the CO2 adsorption. And so you can see 2 metals, nickel and copper, nickel. So this is bimetallic MOF. Before drying, after drying, it has this unoccupied metal sites, and then it is composited with activated carbon. Okay, so these are the characterization. Maybe I'll not much discuss into this. So you can see this is the activated carbon, and this is for the copper MOF. We can see this octahedral structure, and this is copper MOF composited with the activated carbon. And after incorporation of this nickel, its morphology got changed. It has become a rod-like structure. So this is how the material look like. And this is for the composite structure. And maybe this TG also not discussed. And what we have noticed is this is for surface area. So surface area, activated carbon has 576, and which is better with respect to this copper MOF. And after adding this activated carbon, it got enhanced. This is for monometallic, but for bimetallic with 1:2 ratio, after it is composited, the surface area got further enhanced. And what we could notice is this material has porous in material is porous in nature, and even we could see the pore size less than 2 nanometer from this nitrogen adsorption studies. And by this CO2 adsorption isotherm, what we could find was even the pores, ultra micro pore, that is the pore size of 0.9 nanometer could also be observed. So these are helping in absorbing this CO2. So here the CO2 adsorption, these are the comparison between the different materials, activated carbon. And amongst this, what we can see is when it is only this copper MOF, it is 96.84. But after it is composited with activated carbon, it got enhanced. And when it was post-synthetically modified for obtaining this bimetallic, not much change, but with when changing the ratio for 1.2, it is significantly increased. And when it was further composited with the activated carbon, there is a significant increase in. So that means copper MOF alone showed the adsorption capacity for the CO2 as 4.32, which got enhanced to 6.33. So there is a significant enhancement after incorporating that second metal and subsequently compositing with the activated carbon. So this is again, these are two different temperatures. So from this, we can understand this is at 25 degrees Celsius. What we could see is like with the 2%, 1:2 ratio of this copper nickel, compositing with activated carbon of 1% showed a better performance compared to the other materials. So this is like, and we are still continuing on by changing the modifying this MOF material. Instead of using one organic linker, we are now trying with two organic linkers as well. And then we are what to say, it's again like post-synthetic modification or like in situ modification. So these are the different strategies we are trying for enhancing the performance of this MOF material for enhancing the absorption capacity of this material for absorbing the CO2. Okay, so that's all. Like this is an overview of what we are currently doing in our research group. So I think like
Yes, ma'am, you would finish. Okay.
yeah.
Yes. So, first of all, I think I would like to say thank you, ma'am. That is an extensive body of work that you have just shared with us, and a lot of material for these girls to, I think, come up with several technical questions, and I think they would really have a lot of them. I have collected a few.
Okay.
So, if you should I start with them now?
Yeah.
Okay. So there are a couple of generic questions that I want to just take up quickly so that then I can move on to a lot of, I think, subject specific questions that have been, told to me. So just first of all, wanted to start by saying, what has been your greatest motivation to finish PhD? I mean, I'll start from there so that, we can gradually move on to more subject specific things. So I believe you had a lot of challenges while being a mother who is handling a child, and PhD is very intense. So what was it that motivated you to just go on and complete it?
So it is like maybe when we are getting opportunity, uh, we should never miss it, because getting opportunity is that itself is difficult, and especially like when the family is also supportive, then because what I feel is like always like women should be financially independent. To be financially independent, we should for our career, like we should always try for grabbing opportunities. So once we get the opportunity, like we should definitely make use of it, and especially like with the support of family, like when if the system is supporting you, like we should never miss any opportunity. And like of course, as I mentioned, like doing PhD with the kid, it's not an easy task. So it was like, as I said, I can go to the lab. So my work, it was totally dependent on my babysitter. So if the babysitter is not coming, I cannot go to the lab. And of course, it depends on because the supervisor should also be supportive. Supervisor should also
Totally.
understand. So in that respect, like maybe my supervisor, he was very much understanding. But the only challenge was like everything we have to manage alone, because away from family with the kid, and it's all like very difficult. That's the challenging part, because I don't have the freedom of like other what other students have, because many students they prefer working during night time. Even in IIST also, students prefer working during night time. There won't be any
Yes.
disturbance. Without any disturbance, they can peacefully work. But
Yes.
that kind of freedom,
No.
like most of us, we do not have. But that should not be the limitation. That's what I would like to convey. Like whatever the
Right.
limitations, whatever the hurdles, you have to be determined, and you just go ahead, so that it will definitely take you to great heights. There is no doubt
So,
in it.
so you mean these are limitations, but not something that should stop you. So you have to work
Yeah.
around them.
these are the limitations being a woman, like, and especially, and also like, during my PhD, my fellow student used to say like, because she was saying like, I believe that doing PhD before marriage is not a good decision, because like, before marriage, if they are doing PhD, their marriage will be delayed, and also once they are graduated, like once they are become like a doctor, then they have to find equally qualified proposal. These are all like parents' botherations, like. So she was saying like, it's not a good idea to do PhD before marriage. And then after seeing me, then she changed like her mind. It's difficult to do PhD at any point of time for women, before marriage or after marriage. So it has its own challenges. But
There is
definitely like,
no
yeah,
there is no perfect time for, and things should be
yes,
done as
yeah,
along with your stride of whatever you want to do should be done together.
yes. That's why, like, whenever you get a chance, then you don't miss it. Whether it is before marriage or after marriage, it doesn't matter. If you get an opportunity, you grab that opportunity, because, like, I strongly believe that a woman should be financially independent. That is must, actually. So for which, like, you always try to find a way to like strengthen yourself.
And you
So
say
that's,
your family support is there. Who would you think is your greatest supporter in terms of in the professional space? Like I always hear husband or my mother-in-law or mother, but today I would also want to ask you in the professional space, who would you think was the greatest support for you in terms of getting your career further? Because you said that they have to be understanding that you are ready to
yeah.
uh, work around your limitations, but you also cannot do that without the understanding of your PI. So, do you have anybody whom you can say was your greatest support in terms of professional space?
Uh, Professional, like, maybe, as I said, my professor was very understanding, because he always used to say like, you are matured enough, like, because, and he also used to say like, it's for us, like, it's for our betterment, we are doing PhD, so we know like how to handle things and all. So even whenever I had to take leave because of absence of the babysitter and all, like, he never said anything, like, so that much support, that kind of support I got from my supervisor. And he was also like very what to say, like, motivating personality, like. So that is one thing, like, that's really like, because getting a good supervisor for doing PhD, it's most important part in doing PhD, actually. So I, in that way, I'm blessed, I would say. And other than that, my fellow students, because like, sometimes, like, what to say, like, we'll not have like all the facilities available in our department. So during the PhD, the fellow students support is also like very much important. Say for example, like during my PhD, like if I have to perform this morphological analysis, like for this SCM analysis and all, so that usually that is available in the central facility. But if we have to do with that central facility, sometimes like, we have to wait for our slot, which may take month time or so. But if the other labs have that facility, and if fellow students have access to that facility, and so many of the students are also very supportive. And maybe like, yeah, in all these cases, like, I didn't find much of this gender discrimination problem. So only thing is, maybe it's like, life, like personal, uh, because work life balance only, so that is where, like, we find how to, like, being a women, we have some limitations. So that part, like, but it's not always, because many may not have, even have a supportive family also. But what I would say is like, nothing should stop you. Be determined and keep going.
So now I think I'll gradually begin to shift towards the subject specific questions. And
Yeah.
to start with, the first few is that how do you balance very pure academic research with impactful research, which obviously has applications, and they can go very differently. And what are the best strategies for staying updated with these kind of rapid advancement in, say, academic research and in terms of improvisations for creating prototypes and all those things. So these two may go in two very different veins. How do you keep abreast with both the developments? This is in fact a question from one of the students in her
See,
conversation.
actually, this academic research, one thing is like it always requires this, we should get updated. So that's what, so academic research, like we always have to be updated. So we have to follow, read all the recent literature to understand what is the latest development in our research area. But the thing is, what is more important is like, because even during every presentation, because whatever I have discussed, it was all about the electrode material what we have developed for the detection of various analytes. But the drawback of this kind of work is we stop with development of the electrode material. That's it. Even the glucose sensor, whatever I had shown, that stopped with the development of the electrode material, but we didn't fabricate any device. So sometimes that is also essential, because otherwise, whatever that, it will be difficult to fill the gap, because the fundamental research and maybe the product level or the takers. So if that is not taken to that level, whatever the fundamental research we are doing, that may not have much of use basically. So that's why very recently, like now we started working on the development of fabrication of that sensor as well. It is kind of, now we are trying for this wearable sensor. So this wearable sensor, because maybe glucose is already in market, and other than glucose, because whatever I had shown here, ascorbic acid detection. So this ascorbic acid is one of the biomarker for this Parkinson disease. So it's an indirect measurement, and also dopamine can also be measured. So dopamine also we have already detected with our material. So now we are planning to maybe further enhance the performance of these materials, and it can be used for fabrication of this wearable sensor. So that's why always we should uh, try to do whatever the research we are doing, what is its end use so that should also be, because otherwise even I won't say that the fundamental research is of no use, but more than that, we should also think of the end use. So we should plan our work accordingly.
Ma'am, what do you think could be the biggest hurdle in this translational research where you say, I'm going to get it from basic research, I'm going to use this tech for commercialization into some sort of either healthcare or some environmental aspect? What do you think at just the execution level? Because say you are a researcher, to get it from a basic research where you are doing it in the laboratory to going up and saying, no, I want to make this into a product, not with essentially always monetary aspects in mind, but even the doability, like, how can I execute it? Do you have any insights which you can share that what would be your core hurdle if you're a researcher and you're trying to go from shift from this place to that place, basic to
So this
translation?
translational part, if you see, sometimes it requires collaboration, because we may not have expertise with all the, because even our expertise on material part only. So that's why we develop material and we stop there. But to fabricate into device, we need some expertise with the electronics background as well. So it requires kind of collaborative work. So the expertise from different area, they can work together, and because that is very much followed in foreign countries. So the complete problem, if you think, each of the areas will be contributed by the experts from that particular area. So that way, it requires this maybe collaboration from the multiple areas, because nowadays research is highly kind of interdisciplinary. So in that case, we should have we cannot say that because maybe I'm a chemical engineer, but now I'm heading chemistry department. So in that sense, like you should be like free to learn anything, because now it's kind of highly interdisciplinary research. So you have to be
Yes,
ready to learn anything.
that gets me to my next question that I had, that it is getting more and more important to work in an interdisciplinary, collaborative environment these days for anybody. So, how do these students, from a student's perspective, what would it be as one of the good qualities that they should learn, imbibe at a stage, so that they can get integrated into this team in a way that they can grow and thrive in such an environment?
So that's what that student should be ready to learn anything. That is the, and they should be like a, it's a continuous learning process as well. Because from the day one until the end of their PhD, if you see that literature study, so that continues till the end. And when they are continuing their career in research, then it will never end. So they have to keep reading the research articles and related to that area, so that they will get updated. And as I said, like they should be ready to learn any subject. Like now it's also much easier, like we have lot of sources available. That's why, like even in now my student, like who is working on this development of the fabrication of this wearable sensor, she is with electronics background. But though she is with electronics background, she cannot escape saying that I am with electronics background, I cannot read electrochemistry, or I cannot read materials. It cannot be, because she has to learn first, understand about that materials properties, its characterization, everything. And then like she has to go for, and also then it is kind of like when she has to integrate this Bluetooth unit and wireless communication and all, then everything like coding part, like a hardware part and that material part, everything, like if she has to do means, like then she has to learn all these different aspects. So the thing is, students should be ready to learn like anything, whichever the work demands. Whatever the work demands, like they should be ready to learn. There should not be any resistance. So that will definitely help them to excel in their work.
So then there is one question where somebody has asked is, how do MOFs get integrated into biodegradable wound patches to enhance antimicrobial properties and real-time infection monitoring? This is one of our students, Janvi, who has asked this question. Would you have any suggestions right now for that?
Sorry, can you repeat the question?
Can we use MOFs
Uh,
into biodegradable wound patches to enhance their antimicrobial properties? Could there be something developed in this area?
Antimicrobial properties, I'm not sure about, because we haven't like explored that particular area. So whatever the areas we have tried with, for the removal of this antibacterial, like antibiotic, whatever, uh, like all other pharmaceutical waste. So these are the applications, but like this area we haven't explored. I'm sorry, like. I'm not sure
And
about it.
sure. And then there's another question asking, in the case of their applications in space conditions where there is high amount of radiation along with vacuum in the environment, does the MOFs, is there any insights you could provide?
Sorry, like this is with respect to sensing, but vacuum, where is it coming from? I didn't get the
No,
question.
no, the question is that is there any change in sensing properties in space conditions which have got a high radiation and vacuum situation where there is a lot of vacuum in the environment. I mean, the environment it is vacuum. Does that have any change in the sensing properties of MRIs?
So vacuum condition we haven't tried. Otherwise, the other parameters mostly tried or for this, what is the different pH conditions. And different temperature can also be tried, because for this variable sensor and all, like a pH and like this body temperature also plays a role. but like a vacuum we have been tried.
Would it affect the sensing? Would you?
Because I don't like vacuum. How is it important even for the manned space mission also? Whatever that crew cabin, it will not have that vacuum condition. So they will be maintaining the breathable environment and the environment suitable to them. So I don't know how important is that vacuum condition for this sensing applications. Whatever the analytes at least we have studied. So it's mostly like a pH is one another parameter which people focus on.
Then Dhanashri Kadam has asked a question saying that she's working on mono bimetallic MOFs for its desalination application. She's
Okay.
facing some problems with that while synthesis of bimetallic MOFs. So she's facing some problem here. Can you guide her how she can keep in mind some of the things that she can keep in mind while doing this synthesis of bimetallic MOFs?
Okay, maybe you can even share my mail ID with her so that we can even discuss in detail. So,
yes.
Sorry?
It's to an explanation. I'll definitely kind of share the question
actually,
with
synthesis of BMOF, we didn't find much difficulty. But the thing is, for desalination, I guess she must be following that membrane process. I don't know which process she is using. If it is a membrane-based process, so this BMOF, actually, we have also tried incorporating that BMOF into the polymeric membrane and using that membrane for water purification. Again, we have tried with the removal of the ciprofloxacin. And the problem with this membrane-based studies is that to get that consistent result. So, because we synthesize that what to say, that by casting method only we we fabricate this membrane. So when it is done manually, there will be manual error. So sometimes we'll get good results, sometimes we'll not. So that is where we are finding difficulty. So to get the consistent result and to get that repeatability with the less standard error, that is where the challenge lies in polymer based water purification. So desalination is much more it will have its own challenges. So the challenges in this part, and even we are also in the process of fixing that. Otherwise, synthesis of BMOF, we didn't find much difficulty.
So, in any case, I think I should share your contact with this person.
Yeah,
And
sure,
I think
sure.
it will be very nice for you to discuss this in a deeper way. And now there are about 5 minutes still left, and I think I can ask students to kind of ask their questions because there would be small questions about how to do this. And Prerna, for instance, you can just ask your question over here itself. Prerna, can you come? Unmute yourself and just go ahead with the question. Prerna? Okay, anyway, we can go to Pratiksha. She has another question. If you are available and listening, you can unmute yourself and ask a question directly instead of typing it here. Pratiksha Harale?
Yes, ma'am.
Yeah, you can ask your question, please. Go ahead.
Yes. Ma'am, actually, I had a question. I'm currently developing a nanoscale drug delivery system that is meant to target the blood cancer cells present in bone marrow. So I was asking that electrochemical sensing can help us in any way to increase the target specific delivery of the system.
No, I don't think that electrochemical sensing is required for this drug delivery, because usually a sensing, no, how do you, what do you want to sense in that case? Because mostly a sensing is done to maybe find the presence of any analyte. And so mostly the drug delivery is done with respect to the change in the parameter. That is my understanding. Is it not? So that will be detected by its own. You
Okay.
don't require any electrochemical sensor, external electrochemical sensor. Because mostly this electrochemical sensor is used externally, but this drug delivery is happening internally.
Okay, ma'am. Thank you.
Okay.
So Prerna had a question saying, how do you find research fields for pursuing PhDs? Like there are multiple fields. Should we focus on application-oriented research and look for those labs, or she wanted
So
some?
it is like, it depends. Some people like, if they are really passionate about some area, then they can definitely look for the professors who is working in that area. But in my case, I applied in IIT Kharagpur and I was called for the interview and I was given options, with different professors, I was given options to work with the different professors. So I had an interaction with the professors and whichever area was impressive, so that is how I chose. But because otherwise, before starting my PhD, I was not specific about any research area. But when we are interacting with the professor, like I found this because I my PhD work was on plasma modification of this polymers for biomedical applications. That is mainly to enhance biocompatibility and blood compatibility of the polymeric materials. Because when the polymeric material, when it is used for this this applications, biomedical applications, any foreign substance our body will not accept it. It will consider it as a foreign substance and it will not accept it. So to make it compatible, the biocompatibility of the material has to be enhanced, which is done by plasma treatment. So that work was, and it looked more interesting. So that is how I have chosen the research area. Otherwise, it's mostly like if people are interested in, if they have passion to some any other research area, then they can find the professors, those who are working in that area, and find the suitable positions. That's the way you can do. And another thing is of course, you can also the most demanding area also can be thought of, because whichever has scope, so that can also be considered.
Okay. Now, I think there are a few more questions. Anybody who wants to raise a hand and go ahead can also do that. Arishia, would you like to ask the question yourself?
Hello. Yes, ma'am. Hello. Can you hear me,
Please
ma'am?
go ahead.
Yeah.
Yes.
Ma'am, I'm a PhD scholar. I'm basically working on the energy storage device like batteries or some capacitor, super capacitor. So, can you please suggest which
Okay.
material is best, or what kind of scope in this field? Or
Energy storage, it's a vast area and it is the most demanding.
yeah, yeah, yes, ma'am. Yes,
It's
ma'am.
the very, yeah. And maybe which part of that energy storage device you are focusing on is also important. Whether it is an anode material or a cathode material or electrolyte you are focusing on, or what kind of energy storage device, whether it is a supercapacitor or a battery, because all these areas have lot of scope. Maybe, for example, like a lithium ion battery or sodium ion battery. And so what modifications can be done, how to increase the stability, cycle stability, energy density, power density. So there are a lot of materials, lot of scope actually. And even you can think of this fuel cell. So that is one of the applications, like electrocatalysis, whatever we are doing, that have connection with the hydrogen fuel cell. Because for the fuel cell, like again, you have this hydrogen fuel cell. So this hydrogen fuel cell, like how do you get that hydrogen? That matters. And water splitting, electrocatalytic water splitting is one of the ways that we can produce hydrogen. But to produce hydrogen, to enhance this, suitable electrode materials are essential. So this way, it's a vast area. it has a lot of scope, as I said. So, but you have to be focused, whether you are interested in the anode material or cathode material separator, electrolyte, what type of battery, or whether you are interested in supercapacitor, hydrogen fuel cell, or any other fuel cell, methanol fuel cell. So that maybe that requires a little bit of studies as well, because this MOF material is also being used for this energy storage applications. So it depends, like maybe first if you are shortlisting your material, and then you can think of the possible application in the energy storage, or in energy storage, which area you want to focus, and then you can choose the suitable material. So it depends, like you have to work out this combination.
Yes, ma'am. Thank you, ma'am.
So there is Shravani, Shravani Kulkarni. I think you have posted a question. You can go ahead and ask. It says MOF, per MOF, how many metal nodes and linkers will attach, and is decided by which factor?
I think I have seen the question. Can you repeat the question, please?
Per MOF, how many
Ah.
metal nodes and linkers will attach? This is
Okay.
decided by which factor, she wants to know.
So that depends on the coordination number of the metal, whether it is 2+ or 3+, like what is the coordination number, and how it is linked with the, because there are like different structures. Maybe I think I'll. So here you can see, these are the different, depending on the metal node we use and linker molecule we use, because which are the functional groups that are coordinating with the metal node. So depending on that, you will have the different structures formed. The framework, it is different frameworks can be formed by the different combination. So it depends, like we cannot define in the sense like there are a lot of computational studies are also performed, because as of now, nearly more than 90,000 MOF materials are reported, at least theoretically, like and experimentally also they have synthesized thousands, like 10,000s of materials as of now. But the thing is, like if you look at the TRL of the technological readiness level of this MOF material for these applications, it is still in level 6 only, because like the stability issues with this MOF material. But otherwise, like you can synthesize any different structure depending, which depends on the coordination number, like oxidation state or the coordination number of this metal, and whatever the functional groups available in the linker molecule. I think I have answered that question.
Thank you, ma'am.
Okay.
I think that would bring us to the end of the session. I think there has been enough question and answers in this very nice, informative. Everybody's writing that it's one of the most informative PPTs. If may I ask, how much of this information would you be, going to share, or how do we do this? I'll get some questions and then I'll pass it over to you. Is that a better way of
Yeah, sure.
taking up
Yeah, it's fine.
curious questions? Okay.
Yeah.
All right. So I've shared one contact your email ID with Dhanashree Kadam. And if anybody else wants, please let me know and I will share the same. And thank you, ma'am, for your extensive, taking us through the work that you are doing, and we wish you all the best for the future, and hope that you stay connected with Pune Knowledge Cluster for various other, aspects, not just Vigyan, but other aspects also.
Thank you. Thank you. And I hope participants enjoyed this session. Thank you
Yes.
all. Thank you.